Hello and welcome to another of BYJU'S live sessions. Today is the day for physics and we are going to discuss circular motion, friction and work energy power. So in the last session I had discussed briefly, of course because these are brief sessions, I briefly discussed about Newton's laws of motion, and today I'll be discussing circular motion, which is the continuation of that, like the second part of the Newton's laws of motion. You study circular motion and then you study friction and then you go on to study work, energy and power. Now you must have already studied circular motion before, right? Circular motion was there in kinematics. There you must have studied the idea of angular displacement, angular velocity, angular acceleration and all these things. Now what exactly is circular motion, right? Circular motion is basically an object moving in a circle. It's that simple, right? Now what is strange or what is new about it? The thing is, Newton's first law says that if there is no force on an object, right? If there's an object, there's a system and there's absolutely no force on it, then it maintains its velocity. It means that if it has a zero velocity, that means if it is in rest, it will remain at rest. And if it happens to have a velocity which is not zero, which is equal to say 5 meters per second or any constant velocity, it will continue to have that constant velocity if there is no force. That is, if it is moving in a particular direction with a particular speed, it will continue to move in that particular direction with that same speed if there is no force, right? But here what's happening when something is moving in a circle? Now when something is moving in a circle, its speed may or may not change, but the direction of the speed is definitely changing, right? If something moves in a circle, for instance at this moment the velocity was directed in that direction, so it moved, and the direction of the velocity would change. So if the velocity is changing or the direction of velocity is changing or both are changing, the magnitude and the direction, it means that there is an acceleration, right? And if there is an acceleration, there has to be a force. Now what kind of force is this? That's the basic investigation which goes in circular motion. So let me tell you this. I don't have the time to discuss it in detail, you know that, so I'll just touch upon the important aspects and I'll warn you about certain things and all that. So when something like this happens, you have a force which is directed towards the center of that circle in which that object is moving. You have a force which is directed towards the center of the circle, okay? No matter where the object is, the force is directed towards the center of the circle which it is traversing. Now, first thing is that force is called centripetal force. Centripetal, okay? Centripetal means, I think petal means loving or something, I don't know, or directed. So it is a centrally directed force or a force which is directed towards the center, okay? First thing. Now what you have to do is you have to understand that centripetal force is basically a condition for something to move in a circular motion, okay? So given that something is moving in a circular motion, it must have some kind of centripetal force, okay? Now centripetal force is not a fundamental force of this universe. Centripetal force is neither a nuclear force nor it is electromagnetic force. It's not. It's just a condition which some forces may satisfy, and if they satisfy this condition, the object would go in a circle. Simple as that. So putting this in simple words, I can say if something is moving in a circular motion, you have to find the force which is acting as the centripetal force, right? It is going to have a force which acts as if it is the centripetal force, right? So if there's a stone tied to a string and that is like moving in a circle, right? Then what happens? It is moving in a circle because there's a force which is the tension in the string which is directed towards the center. Now this is tension. Now but this tension is acting like the centripetal force which is driving that stone or rock or whatever it is in a circle, right? So a big part of this section is to find which is the force which is acting as the centripetal force. And then the other thing which we learned is that no matter what force is acting as a centripetal force, there is a particular formula in which it should fit, okay, and that formula is mv square divided by r, where m is the mass, v is the instantaneous speed of that object, right, and r is the radius of that circle, okay. So if the tension is acting as a centripetal force, then I can write T is equal to mv square by r, and if it happens to be gravity, then I can write mv square by r is equal to mg, right. So depending on what force it is, you can so basically the step here would be to first figure out if there is a force which is acting as a centripetal force, and if you have found a force which is acting as a centripetal force, then you equate it to mv square by r, okay. So mv square by r is the form of the force or the condition which makes an object go around in a circle. Cool. Now the usual kind of questions which you get in circular motion are questions where something is moving in a circle like that, right. So if I briefly talk about that, if something is moving in a circle, and it's not a horizontal circle, it is a vertical circle, okay. So if something is moving in a vertical circle, then let's take a case when the thing is on the top, right, it is moving, it is on the top. If the speed of the thing at the top is some v, okay, then what would be the centripetal force, or what would be what all forces would be there, or to say like what the thing which we wanted to find out in the first place, what will mv square by r be equal to, okay. How would I figure that out? That's the thing which you want to do, right? And the answer to that is simple, which is like draw free body diagram, and that's the answer to most of the mechanics question. You draw the free body diagram, something is on the top, the tension of the string is pulling it towards the center. Tension of a string can only pull. A string cannot push something. Remember that. A string can only pull things. So the tension is pulling that object in the downward direction, and mg is also acting downwards, because mg always acts downwards. So mg is acting downwards and tension is acting downwards. Does it have any other force in the radial direction? See, you have to make do with your imagination. You know, that's one of the most important ingredients for learning science. So tension is in the downward direction, mg is in the downward direction, there is no other force. So you have got two forces in the downward direction, right, T and mg, and both are adding up. So T plus mg together are providing, at this very moment on the top, are providing your centripetal force. So you can write T plus mg is equal to the centripetal force. And what is the centripetal force formula? mv square by r, okay. So you can say that tension is equal to mv square by r minus mg on the top, right. So when you come down to the bottom, what happens? The tension is acting upwards, mg is acting downwards, right. Now the tension is sort of supporting the centripetal or the circularness of this thing, or its tendency to go in a circle, or it is supporting the centripetal force, you can say, right, to get a feel for it. But mg is in the opposite direction. So now what will you write? You will write T minus mg is equal to mv square by r, right. But now this is the different T, this is the T below, that was the T above, right. So T below will be equal to mv square by r plus mg. So the tension in the string will be more at the bottom than on the top. Now if they give you a condition for when will this string break, so they usually give a condition that the string can take maximum of 200 Newton tension. If they give a condition like that, then you can say that when it goes in a circle, the maximum tension it has is at the bottom. So you can say that tension at the bottom, which is equal to mv square by r plus mg, right, this has to be less than equal to 200 Newton for the string to not break, right. And that's how you, all the values you find out and you put it there, right. So these kind of questions you get in circular motion. Then yeah, mostly things to deal with centripetal force. So the idea here was to understand that centripetal force itself is nothing, it's a phenomenological phenomena. So it's like other forces act as centripetal force given the condition that something is moving in a circle, okay. Now the second thing is friction. Now I really like the idea of friction because and the whole chapter of friction is like can be summarized as this in one graph. Okay, the whole chapter of friction can be like summarized in a couple of lines. It's actually very, very simple. Okay, but you have to be like very aware and clear about what that thing is, no matter how simple it is, because the same simple thing, when they make different kind of questions, the same simple thing, they try to, you know, package it in different ways. But your ability here basically is to take a question and be able to unpack it and find that simple thing in the bottom of that question, and then you'll be able to solve any problem. Okay, now what is the nature of friction? Nature of friction is like this. Okay, friction is like an enemy, but it can only do so much, you know. There is a limit to this enemy, and once that limit reaches it, the enemy gets stuck at that limit opposing you, but you just go on moving. So that's like a weird analogy that I have in my mind. So what I want to say is, okay, so say this is an object. This is my phone. Okay, and this is a force which is acting on it. Okay, now what happens if this force happens to be, say, 1 Newton, and I find that this thing is not moving and there are no other forces but the surface on which it is kept has friction. And if this is 1 Newton, it means that friction is also acting as 1 Newton from the back. It is opposing it. If it becomes 2 Newton, this also becomes 2 Newton, 3 Newton, 3 Newton, 4 Newton, 4 Newton, 5 Newton, 5 Newton, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10, 11, 11, 12, 12, 13, 13, 14, 14. It will go on. Till when will this go on? Okay, so first thing to understand is that friction is self-adjusting. If you apply 1 Newton, friction will say 1 Newton. If you apply 2 Newtons, friction will say 2 Newton. Friction will adjust itself to the force which you are applying. Okay, but this adjustment will not go on for infinity. This adjustment has an upper limit. Okay, now how would you find that upper limit? And in fact, 90% of the friction problems are the problems where you have to find this upper limit. Okay, so you're given a problem. The first thing you do, the first thing I do in most of the friction problems, is I find the upper limit. Okay, or the limiting friction. Okay, how would you find that? It's very simple. Okay, you have a coefficient which is a ratio or a number which is defined for two surfaces which are in contact. It's called the coefficient of static friction. So you have this number, coefficient of static friction, which is a big name for something which very small, which is like mu s, right? It's a very small number, 0.01 sometimes, 0.1 sometimes, right? The coefficient of static friction. So now once you know the mu, okay, which is most of the time given to you in the problem. Now once you know the mu for that surface, right, and if you have an object kept on a surface, what you do is you find out the normal reaction on that object from that surface, right? You find out the normal reaction, not the weight, because weight and normal reaction need not be equal all the time. You must have done these kind of problems in NLM where an object is kept on an inclined plane. These guys are not equal. So not the weight, I'm not talking about mg, I'm talking about n. Okay, so you multiply this coefficient of static friction mu with n, mu n. Okay, what does this mu n gives you? Does this give you friction? No, it gives me the limit to which the friction will adjust itself. All right, so if let's say the coefficient of static friction is say 0.1 for a pair of surfaces, and the normal reaction you find is to be like say 100 Newton, rough example, or okay, say let's say 100 Newton. So what will be the limiting friction? Limiting friction will be mu times 100, which is 0.1 times 100, which is 10 Newton. So it means that till 10 Newton is the capacity of friction. After 10 Newton, friction will be like, bhaiya ho gaya, ab humse nahi ho payega. Alright. Till 10 Newton, friction is all like, I'll adjust, bro. I'll like, whatever you give, I'll like defend. But after 10 Newton, friction is like, okay, not my territory anymore. You have to understand that first thing. So the first thing you do in a friction problem is you find this limit, whether this limit has been crossed or not. right? This is the most crucial thing to understand in friction. So now 10 Newton. So what does that mean? So it means that if I apply a 1 Newton force on an object, friction will be like 1 Newton. I will not let this thing move. 1 Newton, total force 0, no acceleration. 2 Newton, 2 Newton, 3 Newton, 3 Newton, 3.5, 3.5, 4.7, 4.7, 9.3, 9.3, 7.8, 7.8. Till where will it go? 10, 10. Okay. The minute this thing becomes 11, friction is like 10. I can't do anymore. So now this is 11, friction is still 10. Okay. So there is a force imbalance now. So in this object, now there is a net force of 1 Newton acting in the forward direction. Alright. So 1 Newton is acting in the forward direction. 1 Newton divided by its mass, whatever is the mass of that object, say 10 kilograms, will give you the acceleration 0.1 meters per second square. Okay. Now, if this is clear, that friction adjusts till a limit, after that friction doesn't do anything. But another thing, once the thing starts moving, is there no friction? There is friction. But is the friction equal to 10 Newton? Because 10 Newton tak to apne aap ko adjust kiya tha. Now, when you make the force 11 Newton and the thing is moving, is the friction still 10 Newton? So the answer for that is a little ugliness in this whole theory, is that friction reduces a little bit, okay. Instead of being mu s times n, right, which was the limit, which is 10 Newton, it becomes mu k times n, where mu k is called the coefficient of kinetic friction. So this is the friction which acts when something is moving, okay, and mu k is slightly less than mu s. And because we are talking about JEE, most of the JEE problems they give mu k equal to mu s, but you should know, because there are problems where they are not equal there. So, but like as I'm saying, that most of the problems you don't have to worry about mu s being like, they just give mu s is also equal to mu k is also equal to mu, okay. But technically you should know. So what's happening? You find a limit. First thing you do is you find, this is my bar, my limit. Then you do this, equal till you reach that bar. You go above that bar, it means that this is going to remain at the same bar, but once the thing starts moving, slightly the friction will decrease, okay. But even if it once it decreases, it doesn't change anymore. So if something is in rest, and I apply a 5 Newton force, I say how much friction is acting? 5 Newton from the behind, 6 Newton, 6 Newton. But if something is in motion and there is a force already acting, then I say how much friction is acting? Say friction is acting 9.8 Newton, little less than 10 Newton, 9.8 Newton. The thing is moving. Friction is acting 9.8 Newton. Force was 11 Newton. Now I increase the force to 12 Newton. The friction is still 9.8. Now I increase the force to 15 Newton. The friction is still 9.8. Okay. So if this force remains constant, then the friction will remain constant no matter whether this is constant or not. But if this also remains constant, then I can use the equations of motion to solve problems, okay. Or to put this in a different way, by the way, why can I use the equations of motion to solve problems? Because those equations require a condition that the acceleration has to be constant. So sometimes you're given a problem where, you know, something was like some force was acting on something and suddenly the force stopped, because of which it started the friction started acting on it and the object started deaccelerating to zero velocity. So the thing was moving, and while it was moving, the friction was acting on it. So what kind of friction it must be? Static or kinetic? It has to be static. So it has to be kinetic friction, because it was a friction during the motion. And what kind of friction acts during the motion? A fixed friction, a fixed number, okay. So from this point to this point, this is the point from where is your initial point, to this point where the object stops. And if you have to find how much time does it take, I can use equations of motion. I can use v is equal to u plus at. I can use s equal to ut plus half at square, because while motion, the friction is constant, and if the friction is constant, the acceleration or the deacceleration which the friction provides, negative acceleration, as also is going to be constant, okay. So this is by and far the entire theory of friction. That's all friction is. You're given a problem where this block is kept on the table, sideways, upwards, anyway. Okay, there's a ball, there's a fish, there's whatever. Okay, this is the idea you have to remember. The first thing, find the limiting friction. The next thing that we have here is work, energy, and power. Now, see, anything in physics, I cannot do justice to you in 25 to 30 minutes of the sessions that we have. Of course, for that you'll have to download our app and look at all the videos where you also have an aid to your imagination. You have a lot of animation there. But what my purpose of doing these sessions is just to give you a little thumbs up, just to give you a little, you know, a nudge, a little, sometimes a warning, or sometimes, you know, a little advice about how to go about these chapters and what are the things you have to be careful about. So see, you start work, power, energy. The first thing the teacher tells you that this is not the work which we talk about in daily life. It's not like I have got this much work, you didn't do any work. It's not that kind of work. It is the work of physics. It has a very precise definition. It is the force which is acting on a body times the displacement that the force creates, in a rough sense, right? But if the force creates no displacement, then no work is done. So if I stand next to a wall and if I start pushing the wall, and I'm pushing the wall for the whole day and I'm like all exhausted, all my energy is gone, but the wall does not move, a physicist will come and will comment saying that, see, you did no work, you didn't do any work, because physics says that there is no displacement on the thing which you are applying the force. Okay, all that story behind about work. Till 10th standard you have learned that work is equal to force F dot S, right? So this was a very beautiful kid version of things. Now things have become a little more complicated because we are coming to the real world. You're coming to less ideal conditions. So here the F, so F in F dot S, you have assumed that your S is a vector, like things have, the object on which you have applied the force, it has moved in a straight line. Need not be so. Your displacement need not be in a straight line, right? Or your thing might not be moving in a straight line all the while that force was being applied. It could be moving something like this, okay, for all you know. And this formula also assumes that the force which you're using here, for what you used to do, force is 50 Newton, displacement is 2 meter, 15 to 200 joules is the work done. Kitab band, ghar chalo. Okay, you don't do that now, because this force also need not be constant. This force might be varying every second, every nanosecond. This force might be changing, right? So what to do? So in that case, you know what we do is we define the work done in a very, very small interval of time. We call it dW, and dW is equal to F dot ds, right? F vector dot ds vector, where F is the force with that on that object in that very instant, and ds is the displacement in that very small instant, right? Or just that instant and the next instant. So we use calculus to define force, because without calculus we will not be able to define will not be able to get a general formula for force. So that's the one shocker which you get when you start learning this chapter for the first time. Then when you have solved enough problems on work, when you realize that even if the object is having a displacement, but if the force is perpendicular, then literally there is no work done. That is like if you are walking on a road, the work done by on a horizontal road, the work done by gravity is actually zero. If gravity is acting downwards, you are moving perpendicular to gravity, so force and displacement have an angle 90 degrees. So if they have an angle 90 degrees, the work done is zero. You're doing work, but you're doing work against friction, not against gravity. So all those things you learn as you solve more and more problem, and only by solving problem you'll get things. Then you learn the concept of power. In good old days of high school, things were like power is work done by time. Okay, so now if something happens from at t is equal to 1 second to t is equal to 10 seconds, from 1 to 10, whatever work has been done on that object or by that object, you divide it by the time, which is 9 seconds here, done, power, this is power. Okay, now things are not like that, because when a force acts on an object, it is delivering power each second, right? There's a change of power. Initially it was doing more work, or work more fastly, later it is doing work slowly. Okay, so the power itself is changing, the rate at which the work is being done. So you can define instantaneous power. Okay, and instantaneous power has a very beautiful formula. I really love that formula. It is just F dot V. F is the instantaneous force, dot V is the instantaneous velocity. You dot the force and velocity, you get the power. You might ask, how does that happen? It's simple. F dot V, you write V as ds by dt, that becomes F dot ds divided by dt. F dot ds is work, so work by dt, dw by dt, and that's the definition of power as I remember it. So that's power. Then you come to mechanical mechanical energy, right? Mechanical energy, you learn is that is combination of two things: kinetic energy and potential energy. Now one conception which people have is that conservation of energy. They take conservation of energy for granted too much, without understanding the nature of what it does mean when we say energy is conserved. Okay, energy is conserved in a system, okay, but only when there are no dissipative forces. Okay, if there are dissipative, what is dissipative forces? Dissipative forces are thieves of energy. They suck energy, they don't give it back. Okay, so the kind of forces which are thieves of energy, which suck energy but they don't give it back, they're called dissipative forces, like friction, like viscosity. But there are other gentleman forces which take energy from the object, give it back. Okay, these are called conservative forces. Gravitational force is a conservative force, right? Electrostatic force is a conservative force. So what happens in a conservative force? If at this point in a conservative force I start an object, and if I move it around all the way in that conservative field of gravitational field, electrostatic field, whatever it is, and I bring it back to the same point, right? I mean, I'm saying that I am doing work equivalent to the, like there's an agent which is doing work equivalent to the field. It's not like I'm doing an extra work. Or say, or forget about the work which the agent is doing. See, you understand, when you have a concept of work, you ask three questions. You ask, who is doing the work? On what is he doing the work? And the third one that you ask is, I think, yeah, you just ask two questions. Who is doing the work? So I am doing the work. I am the agent. I am doing it. On what am I doing the work? On this thing I'm doing the work, right? So you have to always ask those two questions whenever you're dealing with work. So here I'm talking about, I'm taking a particle and moving it all around, but I'm not talking about the work which I am doing. I'm talking about the work which the gravitational field is doing. This gravitational field is also doing some work. It is also force. So from this point, if I take an object like this in any path and bring it back to the same point, and then ask you, what is the work done by gravitational field? Then you have to remember that gravitational field is a gentleman field. It is a conservative field. So if something has started from a point, it came back to the same point, the net work done by a conservative force or conservative field is equal to 0. It does no work. Whatever work, whatever energy it might have sucked out, it would have given back the same energy. So net amount of work, and you know that work is, energy is the capacity to do work. So there's an interlink between energy and work. I don't have time to go in detail and more precisely on that. So understand that that's a conservative field. But I'm using the word field, you might not be familiar with it. By field right now I just mean force. It's a conservative force. Okay, so friction is not like that. Now if I start from Bangalore and if I go to Delhi, and against friction I'm doing some say I don't think this is like this makes real sense, but let's say I do 100 kilojoules of work. So it's not like when I come from Delhi to Bangalore again to the same point from where I had started, the friction will give me back my energy. It's like, bro, you take your energy, you spent it on me when coming to Delhi. No, I'll again have to spend 100 kilojoules, maybe more. So in this round trip, I lost energy. the work done on me or work done by me on friction sorry, on the floor, or the work done by friction on me, that was not zero. Okay, so this is non-dissipative, so this is dissipative forces, I'm sorry. All right, so dissipative forces, then conservative forces. Dissipative forces are also called non-conservative forces. Now you have to understand that in a system, the total energy remains conserved as long as there are no dissipative forces. Okay, because dissipative forces suck energy and they don't give it back. So that's one important thing, that kinetic energy initial, mechanical energy initial is equal to mechanical energy final only when no friction, no viscosity, no dissipative forces. Okay, then you have the work energy theorem, and that's a very important thing. Work energy theorem says the net work done on an object is equal to change in its kinetic energy. Okay, so you have an object, you have work done on the object, that is equal to whatever is the change in the kinetic energy. Potential energy you don't care, just the change in the kinetic energy. Okay, now the question is, when I said about work, every time you hear the word work, two things should come to your mind. Work done on what? On this object. By what? So the word is net work done. Net work done means the work done by whatever there is. If I am doing a work, I'll consider my work also. If the gravitational force is doing a work, I'll consider that work also. I'll add up all the works which is done on that object, and then I'll equate it to the change in kinetic energy. So that's one important thing which you have to remember in the work energy theorem. All right, so I think my time is up, and I hope this session was a little bit helpful to you in your preparation. Let me see if we have got any questions. So it seems that we don't have any questions right now, but if you do have any questions, keep posting. We try to answer all those questions, and check out our YouTube channel. We have got a lot of interesting videos there, and every now and then we also post fun videos which are important to see, because you also need to know what is the, there's a beautiful aspect to science as well. I know that you're crammed up too much in these 2 years, and do download our app and check out all these videos which we have got with amazing animations and very crisp explanations to all the things, and we have our own practice platform going on there, and very beautiful journeys we create to learn things, right? With that, good evening.